Okay, so now what we're going to talk about is something called Scatchard Analysis, or Scatchard plots. The value of making these, of plotting these, and using Scatchard Analysis is that it is a method to determine your dissociation constant, case of D, when your protein concentration is unknown. Okay? So sort of up to this point, we were saying that you have control over how much protein you put in, right? You had some test tube that had your known amount of whatever your receptor was, and you put in controlled amounts, controlled concentrations of your ligand into that, waited for it to bind, and then did some sort of measurement, fluorescence, radioactivity, whatever it was. And so you had control over both of these things. The reality sort of case is, say you take some cells or some animal tissue and you isolate proteins from it, you're going to get, you don't know how much protein, an unknown quantity of protein. There's some ways to purify this. There's some ways to try to measure protein. But again, if you want to look at binding, when you have a mixture of stuff that is not pure controlled protein that you set up, what do? And so Scatchard lets us sort of put everything in terms of just ligand concentration so that, again, you can control everything. Okay? So let's start with the definition. Our basic relationship for case of D, it is concentration of free protein, concentration of free ligand over the complex. And again, if we make the assumption that ligand only binds to our protein and nothing else, then we could say that the concentration of the complex is equal just to the concentration of bound up ligand. Okay? So we put in some amount of free ligand, some of it binds up, and then the amount that got bound is the amount that is complexed if it binds to nothing else. And so now what we want to do is we want to get an expression for sort of this free or unbound protein. It would be equal to the total amount of protein in your sample minus the amount that is bound up. Okay? We don't know how much it is, but we know that the total concentration has to be whatever's bound and whatever's not bound. And so if I substitute sort of this relationship in here, then the concentration that is unbound is equal to P total minus the ligand concentration that gets bound. And now what I want to do is plug this in to my dissociation constant. So case of D is equal to the concentration of total protein minus the concentration of bound ligand times the concentration of free ligand all over, again, I'm making this substitution here, the amount of bound ligand. So you can rearrange this and get the concentration of bound divided by the concentration of free is equal to concentration of total protein minus the concentration of bound ligand over case of D. So I multiplied this over here, divided by this, and moved KD over. Okay? A couple different rearrangements. And now I can rewrite this in sort of a linear y equals mx plus b form. The concentration of bound ligand divided by the concentration of free ligand, or with our notation, this will be L bound over L. I will say if you see no subscript labeled there, it's talking about the free or unbound concentration. Okay? This will be especially valuable if I give you like old problems to practice with. I'm not going to change the notation on them. And so if there's nothing written, we're talking about the free concentration of these things. Okay. This is equal to -1 over KD times the concentration that's bound plus P total over KD. This here is called the Scatchard equation. This is your y-axis, so concentration of bound over free ligand. Your slope is -1 over your dissociation constant. So again, once you put everything, you're going to have free concentration of ligand, bound concentration of ligand, and when you plot those things, your slope is what will help you get your case of D. Okay. Here's X, and you also then, once you have case of D from your slope, you can plug it into your intercept and get the total amount of protein you had in your sample. Remember, you didn't know this to begin with, okay? But you can get it. So this puts everything in sort of ligand concentrations. So we don't have to know sort of P total going in. Like I said, this is valuable when you have some sort of cell or tissue lysate, so you don't know what exactly you have there, but you can determine it. It makes it easier to calculate case of D because it's linearizing the relationships of free and bound ligand. Okay, and so if you want to sort of look at what this typical plot is going to look like, we're going to plot the concentration that's bound, and then we're going to plot bound over sort of unbound ligand here. Concentrations over here will be, could range anywhere from like milli to picomolar. Kind of depends on what we're looking at. Slope is equal to -1 over case of D. Yep. And your intercept is total protein concentration over KD. And these are going to be, 0.2, 0.3, whatever. So again, this is a way to get your dissociation constant when you don't know how much protein you started with, which is a much more realistic laboratory setting. Okay. I'm going to go into the slides. These equations will be there again, so you'll have an opportunity to jot them down, and then we'll do a couple practice problems. So Scatchard analysis, when you don't know receptor concentration. Okay, so this is the manipulation that I just did. This is the Scatchard equation. Okay. Puts everything in terms of ligand concentration, takes the form of y equals mx plus b, and then the Scatchard plot itself will be bound over free versus bound. This is, again, revisiting, like I said, this will come back. Our sort of important assumption is that we control sort of L total in our binding experiments or in drug delivery. We have the amount of, we can kind of control the concentration of drug that we put in if we know sort of approximately the volume of our blood or whatever it might, depending on the nature of the delivery. And then this is what we're interested in our plots, such as here. This is L-free, and so generally what we want to do is make sure that we have such a high concentration of ligand relative to protein that we can sort of make this approximate assumption such that what we put in is also what's still free. but the equilibrium dialysis case is one where this doesn't apply, and so I will make sure that's known on any of those problems.